Section 1. The tyranny of pressure. We build with steel. We fight the weight of the world, with bolts, with plates, with frames. We think more metal means more strength. But down deep, in the dark water of the abyss, nature follows different rules. It has chosen another path. A path of slow growth. A path of immense size. A path that builds not just with material, but with shape, pressure, and time. We design for the world we know. The deep sea designs for a world that knows only weight. It is a world of crushing, relentless force. Look at this. A small, simple screw. It is tiny. It holds one part to another. Now, imagine that same screw on a submersible, a machine built to descend 6,000 meters into the ocean. The pressure there presses down like 1,000 cars stacked on every single square inch of its surface. That small screw must be part of a much bigger plan. The plan cannot just be harder metal. Section 2. The logic of giants. The first rule is simple, but its consequences are profound. The deeper you go, the heavier the world feels. At 1,000 meters, the water is cold. It is tight. At 4,000 meters, the water is even colder, and it holds more dissolved oxygen. The cold slows down the body's machinery. Its metabolism. A slow metabolism uses less fuel. With less fuel needed to run the engine of life, an animal can invest that energy elsewhere. It can invest it in growing a larger body, more frame for the same amount of energy. This is called abyssal gigantism. It is a simple equation. Cold water plus more oxygen plus a slow metabolism equals a new kind of animal. It is an animal that has more frame and less speed, more structure and less frantic energy. Think of a machine engine. A slow-turning engine with immense torque can pull a very heavy load. It does not need to be fast. It needs to be powerful. The animals of the deep sea have made this trade. They have swapped speed for size. They have large frames. They survive on food that is rare and far between. Their very bodies are re-engineered for this heavy world. Their bones, if they have them, are often thicker, or their shells are shaped in special ways to deflect the crushing force of the sea. They are fundamentally different designs. They are living architectures built to the specifications of an alien environment. Section 3. A fortress against the crush. The Giant Isopod is a perfect example. It looks like a small armored tank from a forgotten age, a relic from a time of heavy metal and slow grinding conflict. 7 overlapping segments of shell cover its back. Each plate of this calcified armor locks neatly into the next. This segmented design gives it both strength and a surprising degree of flexibility. It allows for small, controlled movements between the heavily protected parts of its body. The isopod can curl into a defensive ball, presenting an almost impenetrable shield to the outside world. This is not just armor, it is articulated armor. Under the immense pressure of the deep, these plates press together. The joints do not buckle, they do not break. They are designed to transfer the load across the entire structure. The shell is not thin and smooth, like that of a shallow water crab. It is layered dense and curved. Curves are nature's simple, brilliant way to spread force. A curved surface distributes pressure evenly, preventing any single point from failing. Layers act to stop cracks from propagating. A fracture in one layer does not doom the entire structure. The isopod's armor is a sophisticated design, engineered to handle 500 atmospheres or more of pressure. The material itself, chitin hardened with calcium carbonate, is remarkable. But the genius is in the geometry. It uses the force against itself, creating a structure that grows stronger the more it is squeezed. Section 4. The art of the long reach. Armor is only one answer to the challenges of the deep. The next answer is reach. For this, we look to the Japanese spider crab. It is a creature of impossible proportions. Its legs can span 12 feet from tip to tip. It is the largest arthropod on Earth. But the crab does not run fast. It does not need to. It walks. It uses its long, spindly legs like a delicate crane, reaching out into the darkness. Each leg is a precisely calibrated lever, and a lever is a simple machine that gives you a mechanical advantage. It multiplies force without needing powerful motors. The crab moves its hard limbs from joints that can lock and hold their position with minimal effort. These long limbs allow it to search a wide area for food without having to move its entire heavy body. This is a profound lesson in energy conservation. It costs far less energy to swing a long, lightweight leg than it does to haul a heavy, armored body across the seafloor. The spider crab's design is a masterclass in leveraged movement. The density of its exoskeleton also matters a great deal. The legs are remarkably strong, yet surprisingly light for their size. The shell is thick where it needs to be for protection, but it is layered and structured to cut down on unnecessary weight. The joints are placed at optimal points to use force effectively. The crab is not a machine with a large fuel tank. It is a finely tuned set of levers, perfectly adapted to the pressure and the limited fuel the deep sea provides. They are sensory appendages, probes, and tools. They allow the crab to interact with its world from a distance, minimizing risk and maximizing reward. Section 5. Limbs made of water. Then there are the animals that have all but given up on solid bone. They use fluid and pressure itself as a replacement for a hard internal frame. A squid's tentacle, muscle fibers, and fluid-filled chambers. The Bigfin Squid. The colossal squid are haunting examples of this design philosophy. Their limbs are not stiff beams like the legs of a crab. They are flexible tubes filled with fluid. The fluid, held under pressure, is what gives the limb its shape and structure. But it also allows the limb to bend, twist, and sense its surroundings with incredible sensitivity. This is the world of hydrostatic limbs. The tentacles of these deep-sea squid can curl, extend, and lock into place. Some are armed with rows of sharp, swiveling hooks. These hooks can rotate 360 degrees, allowing them to grip and hold prey with terrifying efficiency. They are like the rotating jaws of a mechanical claw. The squid's arms can bend at sharp, unnatural right angles, forming a vast, sweeping net in the dark water. This net is not just for capture. It is a massive sensor grid. Each tentacle, each sucker, is a feeler, detecting the faintest movements and pressure changes in the water. There is no bone. There is no heavy, rigid internal frame to support. The ocean itself, the very pressure that crushes our submersibles, is used as a tool. The squid maintains a pressure inside its limbs that works with the external pressure of the sea. It uses muscles to change the shape of the fluid-filled chambers, allowing for a range of motion that is impossible for a jointed skeleton. It is a system that is both weapon and sensor array, powered by the physics of its environment. It is lightweight. It is flexible. It allows for silent, stealthy movement. A bigfin squid can drift with its long, elbowed arms trailing far below it, a living web waiting for an unsuspecting meal. The colossal squid can use its powerful, hook-lined tentacles to battle with sperm whales in the crushing dark. Every system, no matter how perfectly engineered, must bend to the fundamental rules of the deep. And the most unforgiving rule is the scarcity of food. The abyss is a food desert, but the sea provides. It provides a feast, but only once in a very long time. When a great whale, a titan of the sunlit upper world, dies, its body begins a long, slow journey down. This event is called a whale fall. The massive skeleton, weighing many tons, sinks through the dark water until it comes to rest on the ocean floor. And where it lands, a city is born. The whale fall becomes the foundation of a new, temporary economy. A sudden, massive injection of nutrients into a world defined by hunger. First, the scavengers arrive. Hagfish, sleeper sharks, swarms of smaller scavengers. Then, the larger opportunists move in. Giant isopods, spider crabs. This stage can last for months, even years. A single dead titan becomes the source of countless lives. But the feast does not end there. Specialized bacteria begin to break down the lipids and oils locked deep inside the whale's massive bones. These bacteria release chemicals, like hydrogen sulfide. Those chemicals feed other, even stranger organisms. Chemosynthetic mussels, clams, bizarre, zombie-like worms colonize the skeleton. The skeleton becomes a reef. The skeleton becomes a habitat. The skeleton becomes a world. We try to map this hidden world. We are explorers by nature. We send down our lights. We send down our cameras. We send down our machines. We build remotely operated vehicles with powerful arms, with high-definition eyes. We drop sensors to the seafloor and listen for the faintest sounds. We bounce sonar waves off the bottom, painting a picture of the landscape in sound. We create grids, we draw lines. Yet, for all our efforts, a staggering 80% of our ocean remains unmapped, unobserved, and unexplored. Our sonar grids show gaps. They show anomalies. We detect shapes that do not match our models of what should be there. A long, thin leg might be filtered out as noise. A layered composite shell might absorb or scatter the sonar pings. Life in the abyss can be gelatinous. Life can be spindly. Life can be composed of complex, non-reflective materials. What happens when the scale of life exceeds the scale of our maps? We stare into the dark and see monsters. But if you look closer, you see the most perfect engineering on Earth. A system that survives because strength can come from flexibility, efficiency can be more powerful than brute force, and pressure can be used as a tool. The answers are there, patient and precise. We stare into the dark and see monsters. But if you look closer, you see the most perfect engineering on Earth. Look deeper.